Thank you. It's so amazing to be here. Like, there's a special place. My favorite conference I've had many times. So let's jump into it, because I don't believe I have 90 minutes, only half of that at most. So I'm going to be talking about how we build Temporal Cloud. And the question is, what is Temporal Cloud? You probably guessed the answer. It's a hosted service that provides temporal technology, the hosted service that provides temporal technology as a service. And if we step back, the question is, why do you need to build it? So if you have an open source server technology, how do you make it sustainable, a sustainable business? How do you monetize it? In the past, there used to be just, you have pay support. People use your technology, they use your software for free, but they pay you to help them with issues. This is a problematic model, even though many companies start with that. The problems are numerous. Like, your customers need to run infrastructure, need to run your software, need to tune it, configure, and then they get to you when they have a problem. So your relations are kind of limited. They don't really trust you to run anything. They just say, hey, we have this problem. And then you discover that they're like 3 versions behind, or the issue you're helping them with for like several days, actually, it's an issue with their infrastructure. So it's not a great model to be with. So the industry has been switching for like the last decade or so to the notion of managed services, where as a customer, you don't have to run the infrastructure. You don't have to have staff that understands how to run it, how to tune it. If you attended Andy Fowler's talk, tuning the database is a massive problem. That's why they have to use ML for that. The same with our other technologies. So managed service requires high trust. So the customers need to trust that you will run well for them. And from security, availability perspective, it used to be impossible. But recently, I think because of the influence of cloud, where cloud vendors taught people that you can actually rely on things like S3, like Azure Storage or EC2, and that kind of paved the way for other companies to say, hey, we can host this, trust us, we'll do it well. There's a third option where they got enterprise services, where the big companies want to give you a lot of money, but they may even give you some limited access, but it has all downsides of the first model, so it's not worth really spending time on it. So when you decide how to build the managed cloud service, there's this dilemma of which model to pick. So the first option is a single tenant provisioning, where, again, many vendors started from. It's like if you host a database, you provision database, like a cluster of database. And it's a good, simple model in terms of you have one-to-one relation between your customer and infrastructure you're running. It's great for isolation, but it's terrible for business. The other option is multi-tenant service, which is much harder to do because you have multiple customers sharing the same physical infrastructure, and they kind of by default don't trust that you isolate them well. You have like noisy neighbor problems, but it's great for business. So I'm explain why. So if this is the graph of the actual utilization, the yellow line of the customer using the resource, the infrastructure needs to be provisioned for higher than that. So the red line is where they need to have capacity to spike if they have like a flood of traffic suddenly, or they have a bug. So you need to have this room for the traffic to be able to jump to. And they have to pay for all of this. So the shaded area is, they pay for this whole infrastructure the whole time, whether they use it or not, which is expensive. With managed service, with the same utilization line, by packing many customers to the same but larger physical infrastructure, physical clusters or whatever you use, you can give them the model of paying as you go just for the consumption based. So that they would pay for this shaded area under the line. And actually, that red line can be much higher than in the first case, because you put all these customers and their spikes of traffic don't correlate in time. They're kind of statistically distributed. And so instead of giving them like 2x space headroom, you can give them 3x, 5, 10x. So it's a win-win for both sides. But on our side, we can put all these customers and essentially oversubscribe infrastructure and sell it many times as opposed to the first model. So that's why it's good for business. And that's what many companies realize, like the MongoDB, like DataStax, Confluent, they all switching from single tenant to multi-tenant models. They also refer to this serverless. I don't like serverless because they're always servers, but doesn't matter. So that's like a learning number 0, that multi-tenant services, hosted services are here to stay. There'll be more of that because that's the good business model for both customers and vendors. So how do we build a service like this? First, we need to decide what we're going to offer to customers, like the unit of our product. What are they going to provision? What are they going to pay for? It's a unit of isolation. Like if you have 3 use cases, you want to have these separate units that don't overlap with each other at the customer. And Temporal, which is Temporal Namespace, is a natural thing for that. I put asterisks about unit of capacity because it's a complicated question. It kind of is a unit of capacity, but it not necessarily, depending on what you mean by capacity. And over time, we don't have time to discuss it. On the back end, it's a unit that you resource manage. You take these resources, virtual resources now, because we don't give a server or a cluster to the customers. We give them virtual resource like Namespace, but we need to map it and host them on actual physical infrastructure. So this like picture of putting these containers of resources into like some physical like warehouse. That's a good analogy in my head of how you manage these virtual resources in the managed service. So from the customer perspective, it looks literally like that. That if they need to connect to the namespace, they configure the endpoint, the name of the namespace, TLS certificates, and then they can connect and execute their code. So no infrastructure, no servers, no clusters, just endpoint, just like you consume like S3 from AWS, for example. They also get this nice experience of having Tiporal UI, where it's for a namespace, they can see the workflows, their state, whether it's running or completed or failed, kind of all the details. So all of that is hosted for them. They don't need to run a single bit of infrastructure to use it. Now, the 2 important terms of, I'm sure many of you are familiar with, but I think it's worth reiterating where they came from. Notion of data plane and control plane. Our industry is notorious for borrowing some terms from other industries. In this case, it came from telecoms. So like you think of your mobile phone provider, you have the packets going from your phone for your phone conversation, SMS messages, or internet. They go through a bunch of physical devices like base stations, routers, switches, some servers. So that's the physical infrastructure typical referred to data plane that's deployed geographically, like all over the country, all over the world. And that's what they refer to as data plane. But that infrastructure needs to be managed. You need to configure it, you need to monitor it, you need to add new instances, you need to remove them. And for that, you need the brain that is referred to as control plane. So control plane, like you need to provision a new switch. Yeah, you configure it, and then you decommission the old one, you remove it to control plane. So there's 2 different kind of orthogonal concerns. One is for actually dealing with traffic, like phone traffic, and one is for managing, configuring, and making the whole system work. And naturally, if you look at the responsibilities of these 2, data plane and control plane, they're different. Data plane, most important, is up. You can send traffic, it continues to be available, it has high throughput, low latency. That's the core of the business requirements from the customer's perspective. Data plane is not on the hot path of processing resources, processing requests of the customers, the traffic. It's mostly about provisioning, configuring, monitoring, managing, all of that. So because of that, it needs to be available, but not necessarily as highly available as data plane. If it's control plane is degraded, some new operations for configuring, creating new resources may be delayed, but the data plane, the traffic is not impacted. Latency is also less of a concern because if you provision the resource, you configure, you don't expect milliseconds necessarily for operation to complete. And naturally, this operation happen much less frequently, so your throughput is lower. So let's look at data plane, how we build data plane. We applied so-called cell architecture. I don't even remember who introduced it and when, but the idea is simple and intuitive. You want to break your data plane resources into this isolated pieces, call them cells, that have one goal: to minimize the chance of correlated failures or some cascading effects of any kind of outages. Like, for example, if the cell catches fire for physical reasons or some software reasons, you want only customers that have traffic going through it be impacted and nothing else. So other cells continue to work. They're not impacted by the outage, and you can take care of it and fix it. Similarly, if on our end we misconfigure one of the cells, you want that impact, their impact, which referred to as blast radius, to be contained to just that cell. But again, only this customer is impacted, only this piece of business, the rest is fine. And it's a common knowledge that the majority of outages in cloud service are because of configuration, not because there's some physical infrastructure issue. So you want it to be contained to one instance. It actually, in Temporal Cloud, we called our units cells. I think Paul suggested that name at some point. So what is in a temporal cell? It's a complex organism. Sorry, Paul. So like each cell has its own AWS account for isolation so that you cannot easily do something across accounts. It has its own virtual network in AWS they call VPCs. It has its own EKS Kubernetes clusters, again, for isolation, so that this cell is isolated as much as possible. In these Kubernetes clusters, there are a bunch of pods around it for a bunch of services. Some are a temporal server. It has its own services like front-end, history, matching, Oracle web, but also we run a bunch of other pods for infrastructure reasons, like for ingress of traffic, ingress controllers, certificate managers, observability. And this is just a simplified subset of what's there. And each cell has two databases that by themselves are clusters. That's why like calling this a cluster would be a misnomer, because there are multiple clusters in the cell in reality. So there's main database and there's Elasticsearch database for like querying the workflows. So of course, this needs to be like provisioned, automated, and deployed. Today we're in the AWS, but we're going to support all major clouds like over time. So in AWS, it looks like this. You have a bunch of cells deployed in different regions. Support 10 regions today, but it doesn't matter. You can support 20. You can support, because the architecture is the same. You have the cells, they deployed, they connected to public network and to private connectivity. AWS, it's called private link for customers that just want to go directly by passing public internet. So that's the data plane. Now let's look at the control plane. I talk about the responsibility, that many responsibilities, like dozens of functions that control plane needs to do accomplish provisioning, configuration, all of that. We don't have time for all of them, so we'll look at a couple of scenarios. So the first scenario is provisioning a new namespace. So it starts by customer going to UI for Temporal Cloud, picking the region, providing namespace name, certificates for TLS to connect, and then they push the button to create a namespace. Very nice, very easy. In reality, there's a whole host of things that need to happen. And this is not a full list. I had to like condense it because of the resolution of the screen. For example, we provision DNS namespace for DNS name for each namespace. Again, for isolation, so we can manage this traffic independently. We need, of course, add it to our database. We need to provision roles for RBAC, role-based access control. Give this user that requested like admin permissions for that, and maybe there are other users. Do all of these operations. For TLS, we need to request the certificates. Like we use Let's Encrypt, so as we use it, like you send the request and then you wait, and they may be available several minutes later, maybe not, maybe you need to retry. Eventually, you configure infra, this ingress controller, to enable traffic with those certificates to go into the service. And the last step is to validate. Does it actually work? Like before you give it to customers, say, okay, your namespace is ready, you want to make sure that you can actually connect, the DNS propagated, and everything is configured correctly. So each of these pieces takes several steps, and they all take time. And they may fail, because of your bug, but more often it's because some other service you depend on is either unavailable, or if maybe something new, giving you like, try later, I'm overloaded, like, Route 63 in AWS may give you throttling error. So if I were to write this kind of code in sort of traditional style, I would be really sad Panda. Because yeah, like no matter how you do it, like, oh, okay, how do you do backup? Oh, I need to like, what if I crash in the middle? I completed half of the steps and they crash. How do I remember where to go from? Nobody wants to be sad Panda, and people that face these problems, they naturally gravitate towards something like workflow-ish, where this problem becomes more intractable. So what is really workflow? It's an abstraction for executing a set of steps, and each one of them can take time, can fail. Like one way to look at it, it's a long distributed transaction. Although it doesn't have most of the transactional properties, but it can be saved. We want to complete the whole thing step by step, and then as they go, we mark them as completed, because we don't want to crash and then restart from the beginning if we completed like 3 out of the 4 steps. So showed here the certificate part. So we request certificate, then we wait and we call maybe is certificate ready. When it's ready, okay, provision routes in ingress with that certificate, and then check, is it ready? Can I connect to it? This is a small subset. So people tend to like go there, and they either, oftentimes they write their own implementation, some kind of workflow agent that's pretty much always a mistake. We have Tiporal is the core product that is workflow engine kind of in its core. And we chose it not for ideological reasons, but because it's actually very good for solving this kind of problem. We look at how we're going to build it. Nobody told us that COD didn't come and say you have to use Tiporal. No, it was just the right tool for the job. And besides this core functionality of the workflow executing steps, Tiporal workflows has a lot more functions. Like, for example, you can start workflow with the ID you give it. And Tiporal provides a very strong guarantee that will not be 2 workflows running with the same identity. It's a very strong guarantee which gives you concurrency control, deduplication, all of that built in. You can query, you can send a kind of read-only request to the workflow, say, give me arbitrary variable you want. You just add a handler and you return maybe like the progress or number failed or whatever you want that communication to be. It's very convenient. You can cancel, of course, if you decided that that operation is not needed anymore. You can replay the workflow, reset it like from the beginning to say, okay, I want to rerun it because of the bug in the code. You can send a message, you call a signal. And for example, it's used for scenarios where you want a human in the loop. So like you have a wire transfer, and if it's over X amount of time, X amount of money, you want to ask to a human, a manager approval, and that human pushes the button, and that sends the signal to workflow, say, okay, this is approved, we can continue that integration. My favorite is signal with start, because when you send a signal, generally like you don't know if workflow is running, but signal with start guarantees that the workflow will be there, because if it's not running, it will be started the process signal. So you can kind of send signals, commands, essentially, assuming that the target is always there. I mentioned like Elasticsearch that allows you to like look and then query for workflows by standard attributes, like with status of failures, of completed, failed, whatever. But you can also have custom attributes. You can, for example, put order ID or customer ID as custom search attribute, and you can just query and say, give me all the workflows yesterday for this customer, and model like that. So there's a lot of stuff that we don't have space to cover. Now, going back to our namespace provisioning scenario, you cannot read it, of course, but this is kind of the whole method. A screenshot of the production code, the method that does this provisioning. And this is, again, you cannot read it, but this is the web UI that shows step-by-step the whole number of steps of execution of this workflow. So we'll zoom into some pieces. The tail end, when we need to validate configuration, we need to validate connectivity to the namespace with provision. So we followed all the steps in the list. Now we need to check that we can connect. So there's a method. This is, like I said, screenshot from production code, validate TLS, which does what? It has this interesting thing. It says, configure activities I'm going to run with infinite retry. Why? Because we don't want to prescribe anything. It's just a policy, keep retrying until the whole process times out, and we can set timeout at the outer layer. So here we just say policy, and we don't write any code to retry, to handle failures like that, or any kind of exponential backup. We get it all for free. And this is like 2 activities that they check 2 endpoints, gRPC and the web endpoint that each namespace get into. If we look at the web UI, we can see that these activities are listed with their timestamps, they input and out arguments, results, and so it's kind of like a very nice debugger at the same time. It's like almost time travel, because they can look at it while workflow is running. We can also look after it's done, and at least in my experience, it's so much better than grabbing through logs, like the text, and trying to find what happened where. It's all structured by this workflow, so you can see like what happens in this execution, that execution. you kind of get this very nice debugger for free. And so when we get back to our list, if we approach this by expressing the same needs in terms of two things, stateless functions we call activities, where you do something, you call the API, it either succeeds or fails, and there is policy what to do with it. By default, we keep retrying. Or workflows. The workflow is a series of steps. There's more than one. It's stateful execution because there's more than one step in it. Because you can have child workflow. Like there are some examples here, like register Namespace DNS. It's a workflow that holds today Route 53 and does its own validation. So it's multiple steps with persistent execution of this activity, of this task. So we can freely combine stateless and stateful pieces of our execution, and the problem suddenly becomes tractable. And you turn into happy Panda, at least I did, and even the red Panda. And this actual photo of red Panda watching Temporal web UI, how the workflow provisioning namespace is succeeding. And there is an intended pun here because Red Panda, the company, is actually a customer of Temporal Cloud, and they use it to build control plane for their managed service. So it's a very nice connection there. And there are other companies. I know that I can mention Red Panda. I wasn't sure about others that use it. So it proves that it's a useful way of solving this kind of problem. So this is the most important learning, that not having to write code to handle transient failures, retries, backoffs, all of that is really liberating. Like as a developer, you write mostly happy path code, and all these kind of orthogonal concerns about failures and retries, they're done with the policy, they're done by the system, by the engine for you. So you write much less code, and the code we don't write is the perfect code because it has 0 bugs. In other words, another way to say it, we gain developer productivity, but also say developer happiness. Literally, we've seen people say, well, thank you, this is so much better. I really love it. We had people that quit their company because they didn't want to use this technology and go to another one because they love it so much for developer productivity. So this is like a scenario where we deal with one resource. But the control plane, of course, needs to deal with operations go like across cells, not just one namespace for one cell. And the most important example is rolling out of changes. It can be a upgrade of Temporal server version or some dependencies, update of configuration. This is the most dangerous thing in the world when you run the service, because if you were to just blast your changes across the whole fleet of cells, you violated the very principle of cell architecture. You really want to do it one by one. And of course, the industry knows that that's what we do, roll and upgrade. Everyone does that. There is the resource management aspect. When you have these virtual resources, you assign them to physical. Sometimes you need to move them. There is load balancing. You decide where to put the resource. All of that is done like with the visibility across the whole fleet or the particular region. So let's look at a scenario for rolling out a new version of Tiporal in our service. So how is it done? The pretty typical approach is to group cells into deployment rings, and people call them differently, different names. They may argue till the end of time whether ring 0 is the lowest or the highest, doesn't matter. Like we organize from ring 0 to whatever the highest number is, meaning that the lower rings are less important, less critical from the business perspective, higher ones are more important. So we go from lowest to important, least important to the highest important. Like ring 0, it's actually a pre-production ring where we don't run any customer traffic, but we have cells that run synthetic traffic continuously under a significant load and have employee namespaces there. So when there's a new version, we want to deploy it there and see if there are any regressions that we didn't catch in testing. And then we progress to the next ring and then to the next ring. And in fact, our customers, like when they create namespace, you can see that they create like dash staging, dash dev, dash prod. So they have different priorities and different criticality for their own namespaces. And some of them actually ask us, can you guarantee that when you deploy a new version, an update, it first goes to my non-production namespaces before it reaches their production namespace? Because they may have their own bug or some kind of weird way that will be exposed in new versions. They want to have the same assurance that the progression happens in that way, literally. So how do we implement this rollout? this is kind of the high-level algorithm where you have loop over rings, and you have cells within the ring grouped into batches. You want to sleep between rings because some of these regressions, they may take time. They may take days if it's like, you leak in memory, or if there is a deadlock that is probabilistic, it needs time to happen, things like that. So for example, after we deploy ring 0, upgrade it, we wait a week. And then we go to another ring, like first production ring. And then we wait for like a day or some cases 2 days between rings. But within the ring, we also have batches where, for the same reason, you don't want to blast a change to all cells in the ring, because again, you violate the same principle of reducing blast radius. The cells are grouped into batches. There are ways between batches. Then you go over each of the cell. And then within the cell, as I showed you, there are a bunch of services, like 4 or 5 temporal services running, depending how you count the web. And so when you get there, you want to upgrade with one Kubernetes service, the temporal service at the time. Like we start with front end, and then we wait, and we have this canaries traffic, right? It's not a synthetic traffic that constantly runs in every cell. And we wait for 10 minutes to see whether any canary failures. Because if something fails, they may indicate a problem that, again, we missed in testing. And if that happens, then we pause rollout and we page on call engineer to check, is that the real issue? Is it something completely benign? Is a false negative, a false positive? And then if that is good, we continue. If not, we stop and roll back. So essentially, this is a giant nested loop of 4 nested loops you need to do. And that needs to run for 7-10 days for each version of it. And again, if I were to write it in a single process, I'll be very sad. Panda, there's just too many things to take care of. And this is how we do it in reality. That when a new rollout needs to start, engineer that initiates rollout, it calls the control plane API, either through CLI tool or through web, say start rollout. For every request to control plane, we create a request workflow, whether it's customer's request, like creating a space, or a total request. That's a nice pattern because it allows you to query what happened with all requests. We keep history, we can query. Again, it's much nicer way to see what happened in the system. You can have alerts if they failed. Very easy. So there's a request workflow that starts the actual rollout workflow, that second green thing there. And that's where this whole thing of massive loops, or the nested loops, is implemented in this workflow, rollout workflow. And then when it goes from cell to cell, when it needs to upgrade a particular cell, it makes an RPC call to an entity workflow of a cell. And I'll talk more about it in a minute. But eventually, the cell by itself, the cell entity workflow, it calls another layer, the infrastructure layer. Their API say, hey, I need to deploy this service to Kubernetes because this is separation of concerns. All operations Kubernetes are handled by that layer. And funny enough, they also implement as workflows because the same reasons. If you do this infrastructure operations, if you call in Kubernetes API, it takes time, it may fail, you may need to retry. So another way is they say, it's like turtles all the way down in our system. Like workflows, they're called other workflows, they're called workflows through APIs, directly because we like it. If we look at the code, this should be legible. This is where it gets batches and then starts looping over batches. So this is an example where implementation actually differs from conceptual picture. It's optimized because there's no need to have a loop over rings. The engineer who was implemented decided, we'll just have a list of batches and they have timing, like the weight indication, depending on which ring they belong to. So collapsed 2 loops into 1. I think it's a good decision. So when we get to batches, we also post message to Slack, and it's just not activity. Post it so people can see what's going on, and then reply change. And eventually we get to this call to invoke a cell entity workflow to invoke to say, again, this is screenshots from real production code. There's nothing it's not pseudocode. So I mentioned entity workflows. What are they? It's actually just a pattern. where you use specific workflow IDs to have one-to-one relation with your real-world entity. Like it can be like accounts, like users, in our case, namespaces for cells. And that's very useful for have this encapsulation of state and operations, for serializing operations to individual entity. For example, when we upgrade with the process of upgrading itself, we don't want to have another upgrade to happen, or we don't even want to have configuration change happen while it's being upgraded. We want to serialize operations, and that's why we do it through the cell entity. Same is true for like user account. When you're making an update, you want to do one at a time instead of some potentially conflicting parallel updates. So it's a popular pattern in general. So it's kind of like digital twins. If like in something inside an IoT, where you have object somewhere that is associated with the device or with location. And when I get to this, like one-to-one uniqueness guarantees, signals to collect and make RPC, I had this deja vu effect because I spent a decade working on actors, and with Microsoft Orleans at the time, we introduced virtual actors. They're kind of the same thing, interestingly enough. So you have these objects that live somewhere in the cluster. You don't specify where, you don't explicitly create them. Just by knowing their identity, you make a call, and that's the object that encapsulates that real entity. So that was an interesting kind of deja vu observation for me, that the stateful computation that they seemed like they move towards the same, the conversion, the same path. Or at least was optimized for kind of low latency, kind of short operations. Tiporal is coming from kind of longer operations like for workflows, but Temporal is adding support for short-lived, their low latency. Paul is working on that, and at least looking to add like support for workflow like longer. So these conversions that happen. So it's probably proves that it's a good pattern. So this is exactly learning that entity workflow is actually a good pattern for like digital twinish kind of scenarios. Now, why Inception? Somebody like some astute listener, observer at the talk probably noticed something odd on this diagram. I don't know if somebody did. If you did, raise your hand. We'll talk later. So the odd thing is like this control plane namespace and info plane namespace, and the question would be like, where do they run? It's kind of chicken and egg question. So if you use the namespaces to run control plane, which cell do they run, and how do they control the namespace? How do you solve this kind of the problem? When I showed you the rings, the deployment rings, I didn't show you the full picture. So like if you shift it left, there are more rings. And the last ring, finding a number 999, doesn't mean we have 1,000 rings. It's just decided to number that one. And it has a cell that runs control plane, info plane, namespaces. And it so happened that we created several data plane cells way before we had the first control plane workflow. So we kind of had where to create namespace. I know it's not a fancy story, but that's the reality. I think it was a practical decision to just bring it up with scripts and some ClickOps, and then automate and have that. So that's the answer how Inception happened. So my micro-learning here is, yes, you can be puristic and make sure everything is just magically happens, but I would argue it's not worth it. Now, to summarize what I was trying to tell you. So first of all, managed cloud services are already mainstream. There will be even more so, I would claim. If you haven't worked on one yet, if you've not been involved, chances are you will be, because that's the sustainable business model for building software, especially server software. And they all need control planes. And we see that with customers, they use that because you have this natural separation of control plane, data plane. Control plane operations, they naturally take time. They deal with failures, with transient, with backoffs, with unavailability of dependencies. And that leads people to implement workflow style, whether they realize it or not. And like I said, pretty much every single person, I don't know anybody to contradict that, but every single person could try to implement their own workflow engine, they regret it later. Because it only looks simple at the beginning, and then as you deal with more and more concerns, you create a huge blob of issues. It's like buying a puppy, that kind of decision. Don't do it with, you buy a puppy, but don't build your own workflow engine. my claim is that Temporal is a great fit for these problems because it's built for implementing this long-running operation that deal with failures, and it externalizes, retries, backups, all of those concerns, which is great. Let's just talk about entity workflows. Consider this pattern. It's great, not just for workflows, but digital twins in general is a great pattern to control like physical, logical, like real-life resources. And then I mentioned that several other customers, only one of them is Panda. They already implemented or implementing the control planes to build their own services. And that, I think, supports my point number 5, that Tiporal is a great fit for solving these sort of problems. So it's kind of like in Inception here. I don't know if you like the movie, but it's kind of like a little bit of Inception here, using control plane, Temporal, to build other control planes. And that's all I had for you today. Thank you very much.